Hey there, my name's Mike, and welcome back to my channel. Today we are talking about a fundamental concept of physics, vectors. If you know what vectors are and know how to add vectors, go ahead and skip this video. This is a supplemental instruction video for our Physics Foundations playlist, and today I pose a simple question to you. Suppose I exist on this two-dimensional flat universe, and I exist right here at point 0 in space, and I need to get all the way over to point 1. How do I do that? What directions do I give an ant or a person in this flat land to go from here to here? Now, the first thing you might think is to draw some sort of arrow here. And if I did, this is about 6 centimeters. But what direction am I telling this guy to walk? If he's facing this way, he's just going to walk 6 centimeters this way. He's going to be nowhere near where he needs to go. So we need a tool called a vector. And a vector is a little different from the numbers that you're probably used to seeing. Typically, when we think of numbers in this world, they have a value to them, a magnitude, and we call that a scalar quantity. The numbers we work with on a day-to-day basis, they have a certain bigness to them, right? Negative a million is negative. I mean, it's still negative, but it's also negative a million. It's a big number. So there is this level of bigness to them, and we describe that level of bigness as something called a magnitude. The magnitude of something. And we use this word in plain English too. We talk about the magnitude of someone's speech or the way they're able to project themselves. Earthquakes are described in magnitudes. The bigger the magnitude, the bigger the earthquake. The bigger the magnitude, the bigger the value of the number that we have here. The more displacement we are away from 0. So that's how we deal with scalar quantities. And like I said, a scalar quantity can still be negative. But my point is, they have a magnitude to them, and they have a sign to them, plus or minus, and that's it. That's it. That's all the number can do. A vector takes numbers and puts them into space. And what's cool about a vector is when you learn how to do a two-dimensional vector, then a three-dimensional vector, you can do any dimension you want. And there's a field of mathematics called linear algebra where you deal with nth dimensional vectors. And you can play with dimensions that are either generalized or four-dimensional, five-dimensional vectors, and it's a piece of cake. You might not be able to visualize it fully yet. Maybe one day in the future we will. But you can certainly play with them and do vector math on these fifth-dimensional entities. And it's really, really quite fascinating. And so today we're going to start the discussion with our problem here. So what we can do is, if we can't just draw a line, we clearly need a direction. So I ask you, look at this grid here. Is there any agreed upon direction? And the answer is yes. Look at these lines here. Clearly, we have what you might call an x-axis here, and we have what you might call a y-axis here. Now, video game developers are going to be very familiar with this. If you've ever tried to write a video game, you do so with x and y. And so when we talk about like writing the physics of coding a video game engine, like if you're doing a side scroller and Mario or something is able to jump up and down, you're able to run left and right. That's your x-axis. You can go negative x, that's just going left. Positive x is going right, and you can jump up and down. And again, jumping up, that's positive y. And as you fall back down, you might fall into a pipe or something and go negative y, down further than where you started. And those are the two, we call them basis vectors. The idea is that any point in two-dimensional space can be some combination of x and y. That's the idea of a basis vector, and we're going to touch more on that tomorrow, so I won't get into it too much. But today, to look at a regular vector, what we are going to do is draw this line, because this was what we want. We do want an arrow that points from P0 to P1, but we want to describe it in terms of directions that everybody agrees upon. And it just so happens that we have two right here. We have x and we have y. So what I could tell you to go from P0 to P1 is to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right here. I could tell you to go positive 11 units in the x direction, and then I walk up 1, 2, 3, 4 units in the y direction. So if I wanted a handy notation to write this line, and we're going to call this a vector, and the way we denote a vector is we put a little arrow on it, because this has an arrow at the end of it, doesn't it? It's pointing to it. We're not pointing from P1 to P0, we're pointing from P0 to P1. So if I want to define this vector, okay, then I might write it like this. I might say v1, and we list it by the components. We agree that there are standard basis vectors, standard directions that we all say, yes, I agree, there is an x, there is a y. So we write it in terms of the x and the y. And unlike a point where we use the regular parentheses, with a vector, we're going to use these angle brackets. And we are going to say that v1 is equal to, we do the x and the y. So just like a point, x comes first. We say positive 11 in the x direction, 4y, or 4 in the y direction, excuse me. So we would write it like this. Another way you can think of this, and this is going to be handy for tomorrow, is that you're also saying you're doing 11 in the x direction, plus walking 11 units, or excuse me, plus walking 4 units in the y direction, because you are adding these two. You're adding this vector here, and then you go up and you add the 4 units in the y direction vector. So these two are kind of like individual vectors, and we call these vector components. If I wrote this on its own, this vector here would just be 11, 0, because we've only gone right and we have not gone up or down. And this vector here, this component, if you will, which we might call Vx, if that were its own vector, would just be 0, 4. And when we add the two together, 11 plus 0 is 11, 4 plus 0 is 4. So we've added the vectors together and we get our main vector that points. This is the idea of a vector. They will always be written like this. Now, really quickly, I want to go over a couple different ways you'll see them written, and we will expand more on this later. But one is you will see them written, this is the vector linear algebra way of writing this, is you might see them written as x and y. X and y. See, it's the same thing. I just want to show you both. So this is the real example of what we just did. Here's x is equal to 11 in the x direction, 4 in the y direction, or more generally, x, y, and that's all the same as doing x, y. Lastly, you might also see them written in something called standard basis vectors. This is going to look confusing at first, so I want you to just understand that this is something people do. Do not understand why they use these letters just yet, but you will also see these special vectors come up, I hat and j hat. And this is like the vector way to write a single unit in the x direction. So I hat would just be one single square I hat. And its vector form would be 1, 0. And j hat would be one square in the y direction, a single unit length. So its vector notation would be 0, 1. And that is j hat. So if I multiply one I hat 11 times, that takes me 1, 2, 3, 4, 5, 6, 7, 8, all the way down to here, and I do 11 times I hat, that's the same as saying 11, 0, which is what I've done. And then we add that to the 4 j hat, 4 times 0 is 0, 4 times 1 is 4, which is 0, 4, which is this Vx, or excuse me, Vy, I wrote that wrong, I'm sorry guys, Vy component there, although it's just a name, so we can name it whatever we want. But either way, we go up 4 times the single unit length. So all of these are equal to each other, and that is the idea behind kind of vector notation, the ways you'll see it written, and what they actually mean, is it is a way to map points in space to each other. Now, we stick with 2 dimensions when we're learning vectors because 3-dimensional stuff can get a little tricky when you're not used to seeing it. And I would like to show you that, so we will do that. Please look in the comments below. You will see the link to the next video where we will talk about the nature of space and apply vector math to it. The last thing we are going to do today is talk about something called vector addition, which we just did earlier, so it's really, really simple. Here is how vector addition works. I'm going to make one vector here that this is our origin, and it goes, looks like 1 in the x direction, and then 3 up in the y direction. And I'm going to add another vector here, and this vector is going to go 1, 2, 3, 4, 5, 5 in the x direction, and 0 in the y direction. Now the way we add these vectors is really simple. And what I want to do is take one vector, write it out again. This is how we do it geometrically. Ooh, sorry for the smudging. We take that vector, and I take the bottom vector, and I move him over so that the tail of that vector attaches to the tip of this vector. We call this the tip to tail method. So I go 5 out, and we have 1, 3, and 5, 0. Now the way to write this mathematically, here's our new vector, by the way. It's going to come here. And he combines where the vector starts and where the vectors together end. And this vector, call it v prime, is equal to the sum. You do 1, 3 plus 5, 0, and you just add the individual components. So now instead of just moving 1 unit in the x direction, we do 1 unit, and then we move an additional 5 units. 1 plus 5 equals 6. Likewise, this vector did not go up or down. We only went to the right, so 3 in the y direction does not change. 3 plus 0 is still 3. And we have now described this vector here. So if I take this vector and I write it out down here, and I go 1, 2, 3, 1, 2, 3, here's 6, and then 1, 2, 3 is 3. What do you know? We have just written the same vector. This one we did geometrically, this one we did analytically with numbers. And so we will typically try and do the number approach more and more often because this is what we want to show you when you do this vector math. But I think that can finish us off for this video. There are multiple examples in the textbook here, which hopefully you've taken a look at. Again, this is the Physics Fundamentals playlist, so take a look. We are reading from the Cutnell and Johnson physics textbook. There are a ton of examples here of components of a vector, vector addition and subtraction. Go ahead and try a couple of these. I will put a worked example problem in the solutions below, and we can kind of, in the next video, I will do a worked example problem, and we can kind of figure out what is ideal to you. What are you looking for to learn? Leave a comment below, and I will make a video on it. I'll see you guys in the next one. Peace.